Now, before we completely finish our conversation of photochemical smog, we need to look at some of the factors that affect the rate of this reaction and the general overall formation of ozone and pollutants from this reaction. So if I take many of the equations and just sort of write a generic net equation for this reaction, the overall net oxidation reaction for VOCs looks something like this, where we have VOCs plus O2, and of course, I've got no coefficients here. This is not balanced. But it's plus O2 plus nitric oxide, produces, in the end, CO2 and water, but then also nitrogen dioxide and more hydroxyl radicals. So the hydroxyl radical that initiates this reaction at the very beginning, even though it's not drawn here in the net reaction, hydroxyl radical is a product of this reaction. And then ozone's not in this reaction anywhere, but we can remember that NO2 undergoes photolysis with the absorption of UVA light to generate a free oxygen atom that then combines with O2 to generate ozone. Now, if you look at this reaction, you'll note that the main two inputs are VOCs and nitric oxide. O2 we assume in the atmosphere to be in excess. And one very important thing to discuss when we're talking about emissions and regulating emissions and attempting to limit emissions, it's important to note that reducing or simply reducing VOC emissions may not reduce the overall ozone concentration or the ozone generated if the reaction is not VOC limited. So we've got two main reactants, VOCs and nitric oxide. If VOCs is not the limiting reagent, then reducing them may not affect the overall amount of ozone generated. There's sort of a nice graph in your text that sort of illustrates this process. So we've got kind of two possible regions, and both of these occur in different cities. So in some cities, you might have VOC limited. In others, such as Mexico City, in other regions, it's primarily NOx limited, which is primarily just the overall concentration of nitric oxide and NO2. And we've got these two regions. We've got the NOx limited region and we have the VOC limited region. Let's sort of go through what each of those mean. First of all, in the NOx limited region, that means that we've got excess VOC concentration. Because we have a high VOC concentration, then presuming that we've got hydroxyl radical around, that means we also have a high concentration of peroxy radicals, and whether those are hydroperoxy or just peroxy radicals shown here. And especially if we're limited by the NOx concentration, that means that some of these radicals here aren't necessarily being turned over by reaction with nitric oxide like they would, or they essentially serve to keep that nitric oxide concentration low, because as soon as any nitric oxide is formed, it's immediately reacted with this high peroxy radical concentration to form NO2 and hydroxyl radical, which then goes back and reacts with VOCs. Now, from this, what falls out is just that the free nitric oxide radical concentration is very low and hence limits the overall rate of the reaction. On the VOC limited side, this is a case where I've got excess NOx, and when I've got excess nitric oxide and nitrogen dioxide, especially in the presence of radicals, then when the concentration of NO2 is high, then we will end up getting combination with hydroxyl radical to form nitric acid. One thing that's really important here to note, and it sort of is seen in this region, but we'll mention it in more detail here in a couple examples, but actually decreasing the nitric oxide or the nitrogen dioxide or just the NOx concentration actually results in an initial increase in ozone, because by decreasing NO2 concentrations, now it's not reacting with hydroxyl radicals, so more hydroxyl radical is available to react with the VOCs and then eventually produce more nitrogen dioxide, which then produces more ozone. It's a little counterintuitive, but that's essentially because of this reaction between nitrogen dioxide and hydroxyl radical that removes hydroxyl radical from the equation. If you actually decrease the concentration of NO2 radical, you end up increasing the overall concentration of ozone. So let's do this in a couple examples here on this curve. So first example is, let's just say that we're on this curve here where point A is, and we're on the NOx limited region, and so on that curve here, the ozone concentration is 160 parts per billion. And let's just look at what happens when we go from 1.2 parts per million to 0.8 parts per million. So here, if I stay on this, if I look here and I just move left to right and I keep the concentration of NOx constant, what I'll see is that I'm almost on the exact same curve over at 0.8 parts per million. So when NOx is limiting, that means that VOC concentration is in excess. So simply decreasing it from 1.2 to 0.8 really has no effect on the overall reaction rate, and thus no effect on the overall concentration of ozone produced. And so there, even though we may have helped air quality a little bit by decreasing those the concentration of VOCs in the air, we haven't affected the ozone problem. Now, as we keep going all the way down to 0.4, now we're over here, and now what we see is, we've kept the nitric oxide concentration constant. Now we see, okay, now we've gotten off of that curve. We're in between the 160 parts per billion and the 80 parts per billion. So we have decreased the overall concentration of ozone as we get close to the point where we've got perfect equilibrium, or not perfect stoichiometry between the two. Now let's do another example though here where we're on the other side. So let's say that we were up at point B and we're decreasing the concentration of NOx. So now we're in the VOC limited region. We've got excess NOx. If I decrease from 0.2 parts per million down to 0.08 parts per million. So here I kept the VOC concentration constant. I started at 160 parts per billion of ozone. Now if I go down to 0.08, I'm about here, which you'll notice I'm actually at a higher ozone concentration than I was when I started. I'm in between the 160 and the 240 parts per billion curves, so I lie somewhere greater than 160 parts per billion ozone, and that's a result of what we mentioned previously. Decreasing the NOx concentration initially causes an increase in ozone concentration. As I go all the way down to 0.4, I get down here to about point C, and I mostly get back onto that curve as we get back into more of a stoichiometric ratio of these two reagents. Now, what are some other things that fall out of this overall discussion on photochemical smog? Well, one is that photochemical smog is not only a local issue. Because of mass transport through the atmosphere, a lot of that polluted air can be transported to rural areas, especially if those rural areas happen to be downwind or in a geographical region. And so rural areas can experience high ozone concentrations without having generated that ozone, simply by having it essentially imported. And this graph of the United States, I think, kind of illustrates that process really well. So certainly, if we look here in kind of the middle region of the United States, Nebraska, Oklahoma, and some of those regions, you can see what we've got is concentrations in the 75 to 80 parts per million ozone this is over an 8-hour period. And certainly not all of these regions are associated directly with an urban center. You'll certainly see some that are, so around the Chicago region and Lake Michigan, where there's a lot of industry, we do see higher parts per million or higher concentrations of ozone there. We certainly see all of the California West Coast is certainly a hot spot for this kind of ozone concentration. Some of that has to do with geography, some of it has to do with industry. And one other thing that I should point out, which I'll sort of mention in the next section, but the US has set the air quality standard for ozone at being 70 parts per million over an 8-hour period. And so what you can see here is that in 2011 to 2013, these are primarily in the summer months, I presume, what we see is that there's significant regions of the United States which are at least at the air quality limit or above. So even if these centers aren't places where they generated the ozone, polluted air can be transported from urban to rural areas. And that sort of leads us into this discussion on air quality standards. So normally those are assessed on over an 8-hour period, although sometimes over a 1-hour period. This is data from 2010, so it's actually a little outdated. The ozone concentration has been updated by the EPA and has been decreased from 75 parts, from essentially 0.05 or 75 parts per billion up down to 70 parts per billion. Or parts per million, I guess, in this case. And some of these other ones, carbon monoxide, which is a partially oxidized species from the oxidation of VOCs. That's certainly a problem. We've got some regulation of that. Nitrogen dioxide, again, that's that brown haze and certainly leads to health problems. We'll talk about that more in chapter 4. Sulfur dioxide, we discussed that some as well. We've got some concentration limits here set by the US and then also the World Health Organization. You can see some comparisons with some other countries here. So this should come out to about 75 parts per billion here. And then the other thing to mention is that when we talk about air quality, it's not only ozone and gas, like homogeneous gas species. Often we talk about particulate matter when we're discussing ozone, especially with coal-fired power plants. We can put out a lot of really fine particles into the atmosphere, which when breathed in can do significant damage to the lungs. And so there's this PM index where PM essentially stands for particulate matter. Then it gets a subscript here, which is essentially just defines the diameter of the particles, or up to the diameter of that diameter of particles in micrometers. So PM 2.5 is all particulate matter of diameter 2.5 micrometers or less. And there's regulation on that because that size of particulate matter is referred to as respirable particles. Essentially, those are ones that are not filtered out by any natural processes. They're small enough to escape all the way and penetrate deep into your lungs, where then they can cause significant problems and be a major health concern. PM10 is a slightly older standard, but is still used. There's slightly larger particles. Now most of the emphasis is being focused on PM 2.5, since the PM10, those particles between 2.5 and 10 tend to get filtered out before they can penetrate deep into your lungs. The last thing to mention when we're discussing air quality is how have we attempted to reduce nitric oxide emissions or VOC emissions. Certainly, we mentioned that in terms of nitric oxide emissions, automobiles were a major contributor to those, as well as other kind of outdoor internal combustion engines, off-road vehicles, as well as your traditional on-road vehicles. And this is where major contributions have come from the implementation of catalytic converters, because they do two functions at the same time. So essentially, a catalytic converter is just a packed bed in this porous ceramic coating that is filled with this catalyst, generally containing small atomically distributed palladium or platinum and rhodium metal. And it's in this packed kind of bed that sits between the muffler and the exhaust from the motor. And essentially, so all of the exhaust coming from the engine has to pass through that. And it functions in two ways. It takes nitric oxide emissions and reduces them back to elemental nitrogen, or N2. And it also takes any partially oxidized or not oxidized hydrocarbon species, anything that's escaped the engine without being CO2. It takes those and oxidizes them further up to CO2. And so it kind of fulfills two purposes. It reduces NO emissions and reduces VOC emissions at the same time. And this has led to a dramatic improvement in air quality in urban centers where vehicle traffic is particularly high. And that about summarizes what I want to cover in chapter 3 on photochemical smog. In chapter 4, we'll dive into some more of the health effects of all of this discussion and and explore some of these concepts in a little bit more detail.